Thank you again, and welcome to the first scientific talk. And so when I was putting this talk together, I originally wanted to give this title, The Unifying Power of Research on the Origin of Life. And the title is a little bit mouth-feeling, and it doesn't roll off the tongue, but then it actually says what I wanted to say, except that when I was thinking about the story that I want to say, I realized that, no, there is much more than just talking about the origin of life. There is a lot more to say if I change the title to Astrobiology. And that is the exact thing that I want to talk about. I want to say that why is it that astrobiology is that powerful? What is it that it does? What is it that it causes us to come here? And put that in the context and tell you how powerful this field is, as opposed to many other fields that you take the field, you go to a conference on planet formation and you see the same 100 people who do that over and over. You go to a conference on star evolution, you see the same people. But then you go to an astrobiology conference, you see entirely different crowd. You have to change the way that you speak, you have to change the way that you communicate, and adjust that to people who are not familiar with your field, you're not familiar with your background. And I'm not talking about an astronomer or from the point of view of an astronomer. If you're a system chemistry scientist, you have to be able to talk to people like me. If you are a geologist, you have to be able to talk to a stellar evolution person. And that is what I want to express. I want to say that why it is like this, and why is it that that help us to have such a powerful tool and unifying discipline. I always put this slide up for two reasons. First, I want to talk about life, and it has a variety of forms of life that we know in it. But more importantly, because my wife sitting over there loves that gorilla with the little flower, and so this is for her. When we talk about life, we talk about, we're not talking about us, we are not talking about me standing here talking to we're not talking about communication with intelligent life, and we're talking about the variety of different life that exists in the simplest form to the most complicated one. And when we want to talk about the origin of life and how we can use that to understand and discover life elsewhere in the universe, we have to come up with its characteristics. And the point of this whole origin of life is that how to define, how to find those characteristics, how to put them together and use that as a tool to identify other places in the universe that may have them. Now, interestingly, we are not the only ones. This whole idea of where life came from, what is the origin of life, and whether it exists somewhere else, existed in the minds of astronomers and scientists and philosophers for centuries. You're all familiar with a variety of different codes and the variety of different research that has been done several hundred years ago, thousands of years ago, to understand where life is from and what it is, and especially when telescope was invented and it was determined that planets rotate around sun, it becomes even more problematic and also more of a question that whether life exists elsewhere in the universe. All those stars that are out there, whether those that are similar to sun, whether they have the capability of hosting planets that will harbor life. And that brings us to try to define what life is. I'm not going to do that. And try to identify its characteristics, and most importantly, the important characteristics that give us a tool to use those characteristics as a gauge and look for life elsewhere in the universe. I'm sure you all agree that when we talk about life, we talk about life on Earth. This is the only life we know. This is the only life we can detect. And our planet is the only life-harboring planet that we know. And these three things that I just said, they are highly connected to one another. If we want to find a life somewhere else, we have to look for something similar to our planet. And we assume that once we find that, and it has some of the characteristics, it will go through the same processes, evolutionary processes, that will make it potential for harboring same type of life. In other words, the key assumption that we make for all our research is that if we find a planet similar to Earth, both in orbital characteristic and physical and chemical characteristics, that planet has a good chance to follow the same path as our planet did. And if the ingredients of life are introduced to it, it may develop similar type of life. And that's our goal, that's our assumption, and then we go after that to see if we can identify signatures. To start, I'm sure you all agree with this, that life on Earth requires these four things. We require certain elements. I'll put some of them up there, CHN, OPS, and carbon and hydrogen, nitrogen, oxygen, and all that. But there are many, many other elements, and we need to have those elements we need it for our life. The elements work together. The chemistry of it works together. It needs a solvent and it needs energy. And in addition to that, there are other physical-chemical processes that must take into account. These three together define a huge range of disciplines and fields that are, at the surface they may not be connected, but at the bottom they're all connected through the fact that they want to address same topic. And then the physical and chemical processes come in to make sure that life evolves, develops, and explain why we are here and how this whole thing happened from the very primitive cells that came to being several million years ago. Okay, so I'm going to give you my view of this, and I admit that I'm a theorist, I'm a planetary scientist, I'm an astronomer, so my view is somewhat biased by that, but I try to put that bias into a productive way, and I try to convey to you the thought process that I have when it comes to the origin of life and finding life elsewhere, and carry you through the logic that is in my head. But I'm pretty much sure that you can tune this to your field and express this through your thought process, and we all end up with the same thing. I assure you, we all end up, the last slide will summarize the whole thing and puts it in the large context. Okay, so we need elements, and we ask ourselves, where do these elements come from? We know that we are living on a planet, and this planet formed from dust and gas in a thin nebula that existed around sun, in a thin disk of gas and dust that existed around sun. The disk went through a tremendous amount of processes. I'm not going to talk about it, and how those processes resulted into a planetary system, and how those processes resulted into formation of terrestrial planet, formation of Earth. But those processes do not necessarily tell us where the elements came from. If you isolate a disk of gas and dust around the star, around sun, and let it go through processes necessary for forming planets, you will eventually, if you form planet, you will eventually form planets of a few elements, like for instance silicate or hydrogen, helium, mostly things that existed in the atmosphere and in the star, and then got distributed to the disk. But where did other elements come from? You have all that periodic table with all those elements, and all of them exist, and many of them are in us, and they're necessary for life. So where did all those come from? So that is where our, me as a planetary scientist have no clue of it. I have to rely on my stellar astrophysicist. I have to rely on stellar evolution, and even going a little bit farther to maybe galaxy astronomers and scientists to tell me that you may be able to get some of the elements from the formation of the stars, formation of sun, but many of the elements that are necessary for life come from the supernova explosion. Now, if you're not familiar with these terms, doesn't matter. As a matter of fact, you are here to become familiar with it. I'm not going to explain what those are, but I just want to throw these words out so you see that you start from the scratch, and then where it takes you, and why is it that this whole thing called astrobiology. So you need stellar astrophysicists, you need galaxy astrophysicists to tell you where those elements come from. And then you get that, you say, okay, very good. I have all these elements, and I put them on the planet, so is it going to start having life? Not necessarily. When we look at life on Earth, we see that in addition to needing elements, it also needs a solvent. We do need a solvent for that chemical reactions between all these elements to work. So that brings the question, where did the water come from? Why is it the question? So those of you who are in the field of planets, it's clear to you. Why is that? For those of you who are not in this field, the biggest question about formation of Earth is that not only how it formed, more importantly, why it has water. Earth is not supposed to have water. Earth formed in a region of that nebula that I showed that is dry. And there should be no water there. But our Earth has water, and not only on its surface, and most likely in its mantle, and maybe interior to that as well. That is the job of our geology colleague to explain that. But the big question is, how can an object, a planet that formed in a dry region, carry water and be able to maintain it? That opens a huge, huge field of planet formation, planet dynamics, celestial mechanics, combined with astrochemistry, cosmochemistry, and all that, to explain just that, where the water came from. Okay, so you put all this together, and you say that, okay, I can explain, I can go ahead and study for years and years, study how water formed, come up with a lot of how Earth formed, come up with a lot of theories and formation of Earth and inner solar system. But the story doesn't end there. So what you see here is a very, very simple simulation of how objects hit each other and form terrestrial planets in the inner part of the solar system. And I'm going to explain to you why we need to do things like this and how this becomes a discipline by itself. I don't know if you can see the red dot there. You know, there are all these big circles down here. These big circles, first of all, the numbers that you see down here is the distance from the sun. Sun is here. And this is 1, 2, 3, 4, 5 AU, and you know, past 5 AU is where the giant planets are. 1 AU is where where Earth is, and 2 AU to about 3 around this region is where asteroid belt is. And you know, Mars is around here, Venus and Mercury and all that. So we want to explain where water comes from, and we start with simulations like this. They're not too difficult, but they open a lot of questions. So you want to form those planets, and you put a bunch of these big objects there. These big objects, they're objects of the size of Mars and the Moon, and they are heavily interacting with each other through their own gravity. Now, if you put these objects there and let them interact with one another, they hit each other, and some of them actually make each other orbit very excited and may push one away. In other words, you let these two interact with one another, and the interaction may cause this one to actually go out of the system. And once you lose it, you're not going to be able to use it in forming planets. So what we do is that in addition to having these big objects that do the planet formation for us, we put these little things down there in the background. You see them. And those little things are small asteroids of kilometer size. We put them over there, and we make sure that they act as a frictional force. So any of the objects wants to go away, they work at a friction, they bring them back in. They lose some of its energy away, so the object comes back in. So I thought to explain these things to just tell you what you are about to see. And what you're about to see is the interaction of these big objects with one another, and how they hit each other, they grow, and they form terrestrial planets. And as this happens, you will see that the issue is not just how planets form, is also a lot about what happens to the asteroid belt. What is the situation with giant planets? Why is it that it's not taking just a few million years? Why is it that it will take several hundred million years to form that? And what happens to the solar system during that several hundred million years? And what is it that, well, this is going to run, and I'm going to stop at, say, here. So what happens? You form some planets, you form other things as well. This doesn't necessarily have to form terrestrial planets or solar system for you. This is just a representative of the physics that goes into those type of models. So you try to explain where water comes from, where Earth forms, and then you end up with many other problems. What happened to the asteroid belt? What happens to Venus? What happens to Mars? What happens to Mercury? And where should giant planets be to accommodate all that? And that by itself become a huge field that even within that field, believe it or not, within that field, people don't necessarily talk to each other. So what I'm trying to say is that it is not uncommon that people doing this don't talk to system chemistries or biologists or evolutionary biologists, the field is so vast and so technical that even within a discipline, the sub-disciplines sometimes don't interact with one another. But the beauty of astrobiology is that it brings all of us together, and that's what I want to get at. Okay, so you try to explain one problem, and many other problems come in, and that doesn't end there. Now, you started to sort of explain where the elements come from. Then you realize that you need a solvent, you need water, and then in order to get the chemistry going, you need energy. And the energy comes from your star, right? But it's much more complicated than that. The reason for it is that the energy coming from a star is not going to hit the surface of the planet, surface of Earth, immediately. There is atmosphere there. So this is a cartoon. I apologize to our atmospheric science colleagues. I use this to explain what happens when radiation comes from sun. So basically, when you have the radiation coming from sun, it's not going to hit the surface. It's going to see that atmosphere, right? So I'm going to, for a moment, please allow me to take Earth away and just fill everything with that little gray thing there, because I want to explain when radiation hits the top of atmosphere, what happens to it. And what we receive is not entirely all the radiation that comes to us from the source. A lot of it results into a chemical interaction between the molecules in the atmosphere. As a matter of fact, what I wrote here, planet's atmosphere is the medium where the stellar radiation is first received, and the process of conversion from ice insolation to equilibrium temperature occurs. So you receive the temperature, receive the radiation. Radiation interacts with the atmosphere, and a lot of chemical composition, and what we receive on the surface is maybe some part of the direct radiation coming in, but mostly because of what happened within the atmosphere. And that brings up a new field. Okay, now, how did Earth get its atmosphere? Where did the atmosphere come from? What is its composition? And more importantly, how do we take the circulation of atmosphere into account? And how is that affected by other planetary bodies with the interaction with the star, with the magnetic field? So once again, you try to explain one, and many other fields come into play. This cartoon is supposed to tell us Earth at the time that is formed, but then as it forms, it cools down. Is it true that when Earth cooled down and broke into pieces and plates, the atmosphere was through outgassing? And how did that happen? How did that outgassing happen? How did that resulted into participation back of water back on Earth? And more importantly, as Earth cools and all this atmosphere comes out, and water vapor tries to rain back on Earth and all that. The Earth cools and then it collapses, and as it's collapsing, many interesting things happen. We get all those plate tectonics. Again, I'm not going to get into that territory to explain that, but you all have experienced earthquakes. So we try to explain. We try to explain the energy. We try to see how much energy do we need and where it comes from, and then we encounter the problem with the formation and evolution of atmosphere, and then we try to address that. We get to the formation of Earth and cooling of Earth and the breaking into plates, and plates are moving on top of each other, and they have plate tectonics, and then plate tectonics helps us to have our CO2 cycle. The CO2 cycle uniforms the temperature around the world. So you start with one, and then it branches all over the place. Each one of these represents a new field, a new discipline, and it's so deep and technical that once you get into it, you know it in the back of your head that this has come from the original simulation that I showed you, but it becomes so deep and technical that although you know that, you spend most of your time just working out the plate tectonic, and you may not be able to talk to me who actually forms the planet for you, right? So the story doesn't end there. So you do all that, and your Earth collapses and it cools down, and plates and everything, but it starts rotating, and it happens to have a core, and it happens to have magnetic field. Now you have the interaction of that magnetic field with your star. How did the magnetic field work? How did it come about? How does it interact? What type of particles it stops? What particles it gives away and it gives through? And how that interacts with the star? What is the magnetic connection between the star and planet and with other planets? Let me give you one very, very simple example of how just the connection between planets affects many things about our life. Planet Venus. This is a simple experiment that your undergraduate students or graduate students can do it with a simple integrator. Take our 8 planets in our solar system and remove planet Venus and replace that with non-interacting objects. Put objects over there that they are very small, like asteroids, like small little comets. And then integrate the 8 planets with those comets in place of Venus. The comets, the asteroids that we put in there, they become unstable. They actually go away. In other words, the system cannot have something in the place of Venus. But put Venus back there and let it interact with Earth, Mercury, and Mars, it becomes stable, and solar system will be stable. Just simple as that. Just one planet affects the entire system so drastically that if it doesn't exist, the whole capability of the neighbor Earth for developing life and being as it is will be affected. So then you have magnetic field. Now you have to go ahead and work on your star. Your star's magnetic field is interaction with the planets. So you're back to stellar astrophysics. You're back to understanding the magnetic field of the stars. That opens another door, another problems by itself. So you put all this together from the perspective of planetary scientists and astrophysicists, you would say that what I have explained to you has all these things, that the life on Earth, everything is connected to each other. You want to explain life, you need to know atmosphere, you need to know the hydrosphere, you need to know plate tectonics and core convection and all that. This is that David Stevenson put this together. This is his view of how life is connected to different properties of Earth and everything. So from a planetary science point of view, this is sort of there. It's not entirely complete. I would add a few more to it as well. But then what I did not tell you is that little piece over there. You know, what are the physical-chemical properties and how do they do that? I'm not going to get into anything. I'm just going to show a couple of slides. I have absolutely no expertise in this field, and I apologize to our colleagues whose expertise is biochemistry, biology, evolutionary biology, and system chemistry. So then, what are those physical chemicals? You talk to them. There is a huge debate on whether replication came first or metabolism came first. And depending on which one you take and it introduces 2 different pathways and approaches on evolution of life and the appearance life, evolution of life, and the chemistry that it carries it. And the story doesn't end here. If you get into, you talk to evolutionary biologists and they tell you all about the tree of life and the different pathways that life took. What we know for sure is that life, when it emerged on Earth, was not like this. It took many, many paths of different characteristics. Some of them sustained, some of them died. And it managed to find different paths, going through different paths and different branches, maintaining and dying and surviving, and finally got its way to become what it is now. And if you do your way backward, try to understand what it is, you end up with a beast like that. Okay. For those of you sitting back there, this is the circle of life. You start from 4,000 million years ago, and that is supposed to explain to you how life came about, not the origin of it, how it evolved, and the evolution, how the evolution got to what we know now. I'm sure that this will be presented in this conference in details, and I'm very much looking forward to it. I've been in several of these conferences in the past 2-3 years, and it's amazing when you listen to system chemistry and scientists from evolutionary biology, how beautifully they explain things that someone like me takes totally for granted. So that brings me to another thing. Okay, so, well, let's wait here. So I explained to you all the diversities, all the difficulties with just studying life as it is on Earth and try to figure out where it comes from and trying to figure out what was its origin. Now, the study is not just that. The goal is not just that. The goal is to use what we have and in parallel to try to understand where it's come from, also look into whether we can find it elsewhere. The idea is that if millions and billions of years took for our life to emerge and evolve, there are many solar-type stars out there with planets around them quite as old as we are, or as young as we are, and it's quite possible that they went through the same processes. But in astronomy, when we say if you find one, there is 1,000. So it's quite possible that we know that there are many, many stars similar to Sun out there, and they have planets. Why not? They might have gone through the same process. They might have had similar supernova happening in their surrounding and injecting all those elements into them. They might have had the planet formation going on similar the way that we did, and the water might have come to them through similar processes. What we know about the formation, evolution of planetary system is purely based on physics, and that physics is universal. So it could have happened elsewhere. That tells us that while we are studying where Earth come from, we can also at the same time identify its signatures and look for it elsewhere. And now we have a ton of those planets to look into. As of July 23rd of 2015, this is the number of the planets discovered by Kepler telescope. I'm going to show the next slide puts all extrasolar planets in the context. But what I wanted to draw your attention to that just from Kepler, during its operation, we got something like 4,700 planets, many of them at the range of 1 to a couple of 3 Earth radii in this regime, with orbital periods of around 300-400 days, 300-400 days down here, right? If you put that in the bigger context of all exoplanets discovered so far, with all different techniques, then the situation becomes even more severe and much more interesting. Now you have several thousands of planets there, and many of them are in this regime of 1 to 2 Earth radii, and with orbital parameters, orbital periods that fall within the 1 year of 360 days and all that. So that tells us that we do have now, in addition to being able to understand where our life came from, we do have grounds and reasons. We have 5,000 reasons to go for it and look for whether life exists elsewhere. But we can't just blindly do that. We can't just go ahead and say, I want to look at the star, a planet right there at 360 days. I want to look at that one and see whether it has life on it or not. It just doesn't work that way. On the other hand, our knowledge is limited. Our knowledge is limited of what we know, and what we know is earthly life. This is the only life that we know, and this is the only life that we can detect, if we can detect. So what do? We have to come up with a tool. We have to come up with a gauge, something that tells us about the characteristics of our solar system, or our Earth and its life, and then be able to apply that to other planetary systems with the assumption that some of them might have gone through all those pathways and finally found the same path that Earth found to have earthly life. It is an assumption that works only in a statistical way, but you don't have the luxury of putting your telescopes over 5,000 of them for the rest of eternity and look for biosignatures. You have to choose, and you have to make your choice wisely. So what do? We define a habitable zone. So you have seen this type of definition of habitable zone. I'm just going to read it. The habitable zone is an annulus around the star where a rocky planet, 1, with a CO2, H2O, N2 atmosphere, basically similar to atmosphere of Earth. 2, sufficiently large water contents, such as Earth water content, these oceans and the water in mantle. 3, and then similar geodynamical properties, plate tectonics and all. 4, can host liquid water. 5, permanently on its surface 6. So you put 6 characteristics over there, very general. You're not specific about them. That is both good and not good. The reason for it is that it is not specific enough, and the reason that is good is that is specific, and the reason that is not good is because it's not specific enough. It doesn't put everything in there, and it doesn't give us a very good, a very detailed tool, but it gives us something that we can work with. I usually don't define habitable zone like this. I define habitable zone as in the following. If there was a strong hand to take Earth and put it around your candidate star, where should it be so nothing will change? So seriously, you know, you want to wake up next morning and you don't feel anything, right? So nothing will change. When you say nothing will change, you are taking all those properties, all those characteristics that results into emergence and sustainment of life into account, but you are not specific. If you want to be specific, you have to pick and choose. You go that way. If you want to be to say it in a way that is correct, but doesn't carry much information, so you do it the way that I define. So when I explained it, I said this is the way that I explain my habitable zone, but it doesn't give you tools to work with. So I introduce 6 characteristics that are better way to use as a gauge. And you use that to identify your planets. Or your candidate planets, and you go through them. So we did this exercise, and within the habitable zone working group with Kepler, we took Kepler discoveries, and we limited ourselves to those candidates that were between that had radii between 1 to 2, 3 Earth radii, and we looked into those that were around with orbital periods around 300 days, 400 days in that area. You see that there is quite a number of them there, and we were able to identify some of them. Okay. If you're interested in the paper, is up there, catalog of Kepler habitable zone planets. We were identified several of them, many of them, and among them we were identified 20 of them that are potentially rocky and potentially and could be habitable, and they are in the habitable zone. Being in the habitable zone does not mean they will be habitable. Being in the habitable zone, even if you can identify water on them, does not mean that they have life on them. It just means that you took one positive step forward to our identifying a better target for your next telescope or your next space mission and all, and that is what we have to do. So there are works, papers, talks that show you many of these may not even work out to be habitable planets, regardless of the fact that whether they are rocky or whether in the habitable zone, and many of them may not even exist. So we identified these planetary candidates and all, and which gives us a pathway forward, but that is where we are. The reason that I wanted to show you this is that in parallel, you develop a tool, you develop a gauge, and apply that to your findings, and in parallel to while you are studying origin of life, in parallel you try to understand whether you can find something similar to earthly life elsewhere. The reason for it is that once you find that, that gives you more than one sample to work with. That's a very good thing, right? You know, what we are doing right now is try to understand how life appeared on this one planet. If you have 2 of them, well, better. You know, you have 1 more. I told you all these things, but I'm going to put them in the context, and I'm going to explain what is the unifying power of astrobiology. So I came about and I said that in order to have life, you have to have elements, you have to have water, you have to have energy, and then so you want to have liquid water, you have to know stars, you have to know planets, you need to know dynamics, you need to know the surface, you need to know the atmosphere and all that. But the story doesn't end here. As you notice, it is much, much, much more complicated. And it becomes a mess like this, that now in addition to that, there are subcategories. How did, for instance, the asteroids come about? How did the rotation of the planet help? And how did the biology come about? How did the isotope abundance and the flux, tectonic regimes and all that? So it becomes much, much more complicated. But what you see is that it gets connected. Everything gets connected to everything else. When in 1998, NASA launched the astrobiology program, prior to that, the program that they had that was only known among a few who were working on that was bioastronomy. In 1998, they decided that they're going to change the direction of bioastronomy and also change its name, and they're going to call it astrobiology. So those who first heard the word astrobiology, they were like, oh, come on, astronomy and biology, what are you talking about? I had the honor and privilege of being part of that founding members, and I was there when my colleagues would say, oh, it's a fluffy thing, you know, you can connect everything to it, you can even connect dark matter to it, you can connect this and that and that. So something that you can connect everything to it cannot be science. And my answer to it was that, exactly. So my answer to it was that, okay, I buy that argument. It is not science, and I don't want it to be science. I want it to be a tool. I want it to be an umbrella. I want it to be a facilitator to bring these things together. I want astrobiology to be what causes all these different disciplines to sit here, to listen to me, to listen to yourself, to listen to each other, and learn from one another. I want this to be my colleague coming here, putting astronomy away, and wanting to listen to geology and biology and try to learn from that to incorporate that to his research in astronomy. So I said to the guy that, no, that's not the purpose. The purpose is not introducing a new field of science. You can take it as a field of science, it's fine. But even if you don't want to take it as a field of science, it is absolutely fine. What is important is that astrobiology puts all that together. And my dear friends, that is the unifying power of astrobiology. Thank you.